geometric quantization of the moduli space of flat G bundles, and now on sigma, or equivalently, if you prefer sigma cross R, it doesn't matter. So whereas this is the full configuration space of fields, which is infinite dimensional, this is the set of classical solutions with respect to the Euler-Lagrange equation that you derive from that. And that is finite dimensional, and it's a symplectic manifold. You can geometrically quantize, and you get something which is mathematically meaningful, which is nice. But if you want to go beyond that, yes. If you want to go beyond that, either for the purpose of having a mathematically solid definition or from the point of view of doing calculations, then it's actually a good idea to just start all over using a different idea. So let me define the loop group LG to be the group of all maps from S1 into G. The configuration space of a string moving on the group manifold G. And so this is a group, infinite dimensional group, and one can consider its representation category. More specifically, what one does is one writes down a particular central extension. The central extension depends on K. So I'm going to put here K to just decorate it like that. And one looks at representations which are projective with respect to this particular central extension. So if I want to say the whole correct set of words, it's like this is a category of positive energy representations of LG at level K. This is a tensor category with respect to the so-called fusion product, which I will not have the time to explain right now. So the alternative to this Lagrangian approach is doing Russiatkinter theory. So this is a combinatorial construction that takes as input a category just like this one over there. It's a modular tensor category. And this category, this construction applied to that category will produce the three-manifold invariance that one was not able to mathematically define up there. So the Russiatkinter construction on a three-manifold M is going to be, well, it's going to be something. I'm not going to tell you what it is. It's just like some combinatorial thing that actually produces a number. Russiatkinter theory also gives the value for the Hilbert space of the theory. And here I want to be actually explicit. So sigma is now a two-manifold. M was a three-manifold. So the way to write it down will depend on a particular pairs of pants decomposition of sigma. And so it goes like that. You have labelings of the S1s. So when you do a pairs of pant decomposition, you're cutting your surface into pieces, and the places you cut along are these S1s that we're going to label by representations of LG, by objects of the category that we're taking. And then you do a tensor product indexed over the various pieces of the decomposition of the surface. And then finally, you write the following finite dimensional vector space, HOM from So lambda, mu, nu are indices for the objects of this thing. These have been labeled because of this step. And then you have this vector space, which is finite. So it's a finite direct sum of finite tensor products of finite dimensional vector spaces. And this is what it is. And now the claim is that these two descriptions are one and the same. And this claim cannot really be verified at the level of the partition function, but it can and has been verified at the level of sigma, and therefore one can take the point of view that this is the mathematical definition of this path integral, which otherwise is a bit difficult to define. So now on the Russiatkinter side of the story, there's one thing which is staring at you in the face and which is not present up there. And that is this category here, this category rep K LG. And from a physical point of view, this is the category of possible charges of Wilson lines. From the mathematical point of view, this category is the value of the theory on the circle. So I will just write it like that. I will write it, this is Chern-Simons theory on the circle. And you should think of the circle as being transverse to the Wilson line. If the Wilson line is going like that, then the circle is sort of wrapping around, whether that helps or not. So this idea that TQFTs should have values on manifolds of various dimensions, here we have M of dimension 3, sigma of dimension 2, the circle of dimension 1, that's called extended TQFT. So let me tell you a little bit about extended TQFT. So to a 3-manifold, a TQFT. So I'm doing the thing for dimension 3 theory, so 3-dimensional TQFTs. To a 3-manifold, one has the partition function, which is a number. To a 2-manifold, one has the Hilbert space, which is a vector space. To a 1-manifold, as we have seen over there, we have a category. Okay. Possibly, one can also encode a category by the data of an algebra. So it's okay if you have an algebra as the value of the theory on a 1-manifold, because an algebra and a category are kind of the same thing. Given an algebra, I can take its category of representations. So, and to a 0-dimensional manifold, well, the recipe says that it should have a 2 category. But again, for the same reason, you can also take this to be a tensor category. Then you don't need to think about 2 categories. So this I cannot use. So one shouldn't just have values for closed manifolds, but also for manifolds with boundary. If I have a 3-manifold with boundary, so here I have some M3 with boundary here, then what one should get associated to that is a linear map, the propagator, a map from the Hilbert space here to the Hilbert space there. And if you have a big 3-manifold, which is given to you and you take it and you cut it into pieces. You sort of like cut it into pieces. So each piece sort of is going to cut it, and you're going to see a Riemann surface here and here and here. What you end up seeing is a sequence of maps, of linear maps, that you can go ahead and compose. And if you take those maps and compose them, you end up with a map from the thing associated with the empty manifold, which is just the one-dimensional vector space C, the complex numbers, from C to C. And a linear map from C to C is a number, and a number is exactly what we want for a three-manifold. Same story, one dimension down. If I take a cobordism between one-dimensional manifolds, then, well, here I had a linear map. Now I want, if I think in terms of categories, I'm going to say I want a functor. If I think in terms of algebras, I'm going to say I want a bimodule. So it's a functor or bimodule, depending on preference. And same story, if I have a Riemann surface which is about to be cut into pieces, so I cut it into pieces, then I have a number of functors that I can compose, and here I get a functor from the trivial category. What is the trivial category? It's the category vec, the category of vector spaces. And a functor from vec to vec, you need to think a little bit about that, but that's the same thing as a vector space. So, or if you rather prefer, you can take bimodules, and then you can compose these bimodules, and again, you get a vector space. So that's a way of recovering the Hilbert space from smaller pieces. And the idea of extending a theory all the way down to points is the idea that the same should apply when I take a circle and I cut it into pieces. There should be a way of recovering this category from other more elementary pieces that will, when put together, recover this category. So there's a, let's see. Why is this important? So it's important because of a theorem called the Composite Hypothesis. So this was first proposed by Baez and Dolan, and then proven by Jacob Lurie. And this theorem says, let me put here Lurie. This theorem says that a TQFT, provided it fits into this extended formalism, is entirely determined by its value on a point. Yeah, so you need hypothesis. So I didn't say that any possible value on a point is going to produce a TQFT. I said it's determined by its value on a point. It so happens that some values on points are not allowed. So yes, the possible things that are allowed are the ones that are fully dualizable, as you're correctly saying. Yes? Well, if that was an assumption, then I wouldn't be here talking about this. So, yeah, so it was believed by a number of people that what I'm about to tell you now is actually impossible to realize for exactly the reason that you're saying. So what does this mean? Whatever Chern-Simons theory on a point is, it's going to be something that contains in it all the information of Chern-Simons theory. It's something which is, I mean, just like the Lagrangian, it's like something that if you just give that, you know the whole thing by looking at it in a correct way. So I have a proposal for what that should be, but let me first write down a definition. The base loop group, omega g, is the set of loops such that they're based, meaning there's a chosen point on S1, and that chosen point needs to go to the identity engine. That's a group. So the proposal is to let the category of representations of omega g, and again, you want to take central extension, just like as above, to be Chern-Simons of a point. So this is the proposal which I'm making. So here. So now I already told you what the value on a 3-manifold is. That's the partition function. On a 2-manifold, that's a Hilbert space. On a 1-manifold, that's the set of possible charges for Wilson lines. And I would like to tell you what, to the best of my understanding, what the physical meaning of this thing is. So I'm not 100% sure of what I'm about to say right now. So I'll just say it, and you shall be just warned that I'm not 100% sure about it. Let's see, is there a way of bringing this higher up? No, doesn't work. Therefore, okay, let's see if this works. Oh, no, that didn't work. Sorry for that. I thought it was possible. Great. Then I'll do it here. So what are the objects of this category? So these correspond bijectively, except small question mark, because I'm not sure that this is actually completely correct, even though I strongly expect that, provided you put appropriate hypotheses, this will be a correct statement. These correspond to line defects for chiral WZW theory. So if I have my Chern-Simons theory, which lives on some 3-dimensional bulk, so here I have Chern-Simons theory, I can put a boundary condition. Well, it's an old idea that this theory admits a boundary, which is the chiral WZW model. And now what I'm saying is that line operators that are entirely contained inside this boundary are the objects in here. And, well, maybe this is only true for the dualizable objects in here. This category is fairly big. It contains lots of non-dualizable stuff. And maybe I should say I only take the topological lines, and those correspond to the dualizable ones here. Not exactly sure. This is something that, by the way, is mathematically completely defined. I know exactly what I'm talking about. So whereas line operators, I'm not completely sure exactly how to pinpoint it down. But anyways, this is somehow an intuition for what this thing might be. And by the way, this is a tensor category. It can fuse lines together. And whereas the thing upstairs is a braided tensor category. That one is only fusion. This category contains in it lots of stuff. Not everything in it is dualizable. But itself, as an entity, itself is something that is fully dualizable. But it contains inside it infinite things.
Thank you very much.
David. So, is this really true category?
I'm sorry?
So, line defects typically, endomorphisms or line defects in these WCW models will presumably include local operators in the WCW model, right?
Sorry, I did not understand what you're saying.
Is this working? Yes. So, endomorphisms between line defects.
Yes.
Will be things that look like local operators in the WCW.
Yes.
So perhaps we'll have conformal dependence on the position rather than topological.
So the objects of this category, if they correspond to lines, then the morphisms of the category correspond to operators that live at a given point on this line or possibly between a line and another line.
Yes.
If I made my line be a topological line, then it makes sense to only look at topological insertion points.
Do they exist?
Well, if your line is irreducible, there's going to be only scalars. Okay. If the line is not, then there's going to be interesting things. But it's interesting to also allow things that are not irreducible, because when you fuse things, then they become non-irreducible. So if you have a trivalent vertex, then yes, there's going to be interesting stuff. If you just have a...
Could you describe this mysterious category of omega G for the case when G is just U1?
It's not easier to describe in that case than in the general case. It is easier to do it, and I can do it when G is a finite group. If the G is a finite group, then this is not the correct way of saying things, actually. But what you end up, once you say it in an appropriate way, what you end up having is the category of G-graded vector spaces. So this is when the group is finite. When the group is, well, anything, what I can do for you is give you a family of examples of things that live in here, which possibly will help you. So first of all, if I take a representation of LG, I can restrict it to being a representation of this subgroup. So that's already a source of things. These are like the lines that come from the bulk. But another source of things that I can put in here is twisted representations of LG. If you give me an automorphism of G, then there's the notion of a twisted representation. That's an instance of something that's in here. That's like, but there's more.
Correct.
What's the relation to von Neumann algebra?
Well, the relation to von Neumann algebras is that this is the way in which the fusion product is defined here is via the corresponding notion of fusion of bimodules for von Neumann algebras. So, yeah.
How should we think of those von Neumann algebras physically? Are they generated by chiral operators and by chiral currents? Is it an operator algebra?
Yes. So if you take the category LG and want to equip it with a fusion product, there's a number of things you can do, but one route which is going to actually extend to this situation, and the other routes I don't know how to extend them to this situation, goes via von Neumann algebras in the following way. You take your loop group LG, you look at the subgroup of loops that are supported only on one side, generated von Neumann algebra with that, same thing on the other side. A Hilbert space with an action of LG becomes a bimodule for these two algebras, and composition of bimodules is the fusion. This... Yes.
So you take the weak closure in the basic representation of the loop group?
Yes. You do exactly that. You take the weak closure of this group of things, of loops supported here, the weak closure of loops supported there. Those are von Neumann algebras. They're defined on the vacuum representation, but they will act on any representation, positive energy representation of the loop group. That's a non-trivial fact, which actually is only known in some cases and not in all cases, even though it's expected to always be true. This story then extends to this thing, because when you do this thing, there is a particular point that you end up never touching, which is like the point up there. And so whether or not you have base loops or not base loops, it doesn't matter, because this is not this part of that the von Neumann algebra doesn't see.
Okay, maybe we should call it a day. I think people can keep discussing informally. But thank you very much, everyone, and thank you for keeping time.